Okay, here is Matthias. Money. You will hear about the money a lot in this talk. All right. Good morning to JFocus, day number 2, and good morning to the only session in JFocus when I'm going to give you money. I know it doesn't look real, but wait and see. Wait and see. All right. Okay, so what we are going to talk about? We're going to talk about a lot of those, how hard it is to write concurrent HTTP application in Java, a lot of those, why didn't we use something obvious, and a lot of those things that we thought that we might use and apparently we couldn't, and also it will be a lot of beers, not the beers from last night, this kind of beers, and there will be a lot of questions as well. And for those questions, I will throw frogs on you. Where are my frogs? Somewhere there. Oh, okay, here they are. Okay, so I have bag of frogs. You cannot deliver a talk without bag of frogs. So I have bag of frogs, and I will throw frogs on you, and some frogs will contain money attached to it. So be focused. It's JFocus after all, and you have a good chance to win some money, actual money. All right. So this is me. My name is Baruch. J Baruch at any possible social network, and I'm a developer advocate with JFrog, and this is JFrog, a startup company based in Israel, California, and France as well. We are obsessed with frogs, as you might already noticed, and we have two products: Artifactory, which is a binary repository, and Bintray, which is a distribution platform. The common thing with those two, both of them serve binaries. We basically give away jars for people. This is what we do. And we have also, except of having those two server-side products, we have satellite projects which are essentially clients, right? So we have CI server plugins which download the binaries. We have command line tools which download the binaries from our two main projects. We have clients written in different programming languages, Java clients, which download binaries. All those download binaries, and the single feature they all don't have is concurrent downloads. Right? So if you have a Java client that now need to consume binaries from Artifactory, it will do it file by file, one after another, which is nice, but of course concurrent downloads will be actually better. So time has come, and last year we decided that we want to add concurrent download capabilities to all of those clients. Of course, we were about to write a library that will do a concurrent download from Artifactory and Bintray, and then embed this library into each and every of our clients, including maybe an applet for a browser. We didn't write applets for a long time, 15 years, and we kind of missed them, so it's time to write a new one. This is the list of the requirements. Of course, naturally, parallel file downloads, many files in parallel file parts. So if you download one file, it could be split it into two and download in parallel. Interrupt, pause, resume functionality as well, and progress bars for downloads. And one additional feature that we won't discuss today, but it's also very, very important, is the checksum caching. So both Artifactory and Bintray, they use checksum-based storage. Eventually, if we send the checksum in front and we discover that this file already exists, we don't need to download it at all, right? Which is kind of nice optimization. You want to download the file and boom, magically is already there. So we won't talk about the checks and all this stuff. For all the rest, we're definitely going to do that. Now, a part of this last bullet, when you see this list, what the first association you have in mind, you say, okay, I saw it for sure. I know what is it. I know what concurrent downloader is. Those guys, right? Add-ons, extensions, plugins for browsers that do exactly that, right? Download files in parallel, download file parts, etc., etc. Very familiar for all of us. And then we said, okay, let's see if we can reuse one of those. Can we take the source code? Can we grab some ideas? Can we use something from those? And we found something that was actually written in Java, and it's called the Java downloader. And it is indeed a Java downloader, supports multiple downloads at a time, etc., etc. More or less all the list that we need, and it was looking very good, but then not so much. So what happened? Why we didn't stick with JDM? First, it has no license. Apparently we want to look at the code, we want to take the code, we want to change the code. If there is no license, it doesn't mean that we can do whatever we want. It basically means we cannot do anything. So that's the first problem. Other problem, we didn't find any documentation whatsoever. And slight problem, we didn't find sources. So it was kind of challenging to embed it. Take it as it is, wasn't an option because it's an app and not a lib. We could use the sources, but we didn't find sources. So, no, we didn't take it, which basically means if we want concurrent downloader, we need to write it for ourselves. So this is what we did, and let's see what we have in mind. First idea is URL connection. And that's a really bad idea because Java.NET URL connection buffers everything it does into memory. It's extremely memory wasteful. Almost have no API. You can just open a connection and get a stream. That's all you can do. The streams are blocking. So definitely not an option for us. Mainly because of the blocking stuff. Of course, we needed non-blocking API, so we could actually implement downloading a lot number of files and parts over minimum amount of threads. So what do we do when we need a non-blocking API? This is the first requirement. We also need event callback, so we could provide a progress bar. And apparently in Java, when we are talking about non-blocking API with event callbacks, we have to use those two. Something that is called a reactor and something that is called Nile. Let's start talking about the reactor. Reactor is nothing new. It's actually a pattern which exists for many years now, and it's a pattern for lightweight concurrency. It is event-driven, which means you get callbacks when something is happened, and then you can process it in the single thread. You reuse the threads because you process those events from multiple parallel things that happen inside a single thread, and it uses non-blocking I/O. So this is how the patterns looks like. This is a very boring URL diagram, but it's actually quite simple. So what you see here is that we have this dispatcher that is handles event. This is kind of the pseudocode of this handle events method. Well, actually it loops over handlers and select a good handler for this type of the event, right? And the handlers, they just register themselves in beforehand for the event that they are interested, and when it goes, when the events start coming, this dispatcher just selects who is going to process what. So, but this is a boring slide. This is much nicer. And here is the first question for money for you. Guess the author of the diagram by how it looks like. Come on, guys, you should know. He is a celebrity. Thank you very much, Dave. And we got started. Indeed, this is, of course, Doug Lee. And this is one of his first talks about... Should pick it up, because that's money. This is one of the first diagrams of his first talks about the Reactor pattern. This is a server side. This is a server side, but it's actually the same. So here we have the Reactor itself with the dispatching thread that emits different kind of events. And then we have some kind of selector that selects what went here. Now, why Doug Lee would explain a Reactor for us? Of course, because the Java implementation of a Reactor contains NIO. We're going to talk about it in a second. But let's get back for a second for the Reactor. And this is the actual diagram of how it works for our perspective, from the client perspective. So clients get connected by opening a socket channel for everything that they want to do, and then they register themselves for different operations, right? So this selected themselves for the yellow operations, and this for the red operations, and this for the blue operations. They got registered, and now there are events coming from the server, different kind of events, and the selector knows how to select which handler should take care of which operation depending on the type they registered in front, right? This is it. It's not a rocket science, but it's a very, very powerful pattern that allows very cheap concurrency. Since we don't need to keep a thread for each and every of the customers, of the clients, we actually have a single thread that dispatches the event, and then threads as needed when there are events. But when there are no events, you don't need any threads to work at all. And this is the minimal implementation with Java. So the first part is creating a socket channel, etc., etc. That's okay. And here is the interesting part. We have a selector, and then we say you shouldn't be blocking at all. This is the whole idea, not blocking concurrency. And then here comes the registration, right? So some channel, this is a client, registers itself for a selector with some type of event, selection key. So this guy said, okay, I want to read. This is the operation I am interested in. Okay? And then it attaches a handler, which means what operation should be done when an event of such kind that I'm interested in is coming. Right? Pretty simple. And here is the dispatcher thread. So it loops forever and waits for any kind of event. This is a blocking operation. It sits and waits until any kind of event comes in. Once there is event coming in, then we need to select who is going to take care of it. Okay, so here we got the selected keys, and we check what's the correct selection key is. Take the attachment, which was an operation that need to be performed for this key, and just run it in a thread that we took from a thread pool. Okay, so this is exactly what you saw in the diagram. There is a guy that actually selects who should be dealing with this kind of operation. The only problem with this code is that it's very, very low level. And wiring it up for our needs will be very, very challenging. Okay, handling all those events is complex. First of all, we need to maintain state. Think about it, we have files, we have file parts, interrupted, paused, chunks that we need to build together, etc., etc. A lot of state to maintain, right? Buffering for assembling the chunks. We need to keep the partial files somehow, and we need to coordinate the async events so the new chunk of file will be successfully attached to the correct file and not to some other file. So basically, this is a very, very low-level stuff. We would prefer to have some kind of framework on top of it. And there are many. So, another question for 100 kron is, who knows what NEO stands for, except of the new IO or non-blocking IO? Yeah, okay, that was a very hard one. It took me Wikipedia to find out. Neo is a guardian of Buddha. Now you know. And except of guarding the Buddha, it's also the non-blocking IO, and there are a bunch of frameworks that do the heavy lifting for us in working with the reactor pattern. And there are a lot, and we had to decide. So let's see what they are. So first of all, most of them are for the server side, and of course the reactor pattern is mostly used in the server side, and of course most of the frameworks are dealing with that. The examples of the server side are Netty, Grizzly, etc., etc. Well, we recently discovered that Netty does have a client side co-part, but it's not very maintained, so you know Netty for being a server side, and that's where they put most of their effort. Apache Mina, which is a client-side framework, and Apache HTTP components, a new project inside them, async client, and the Nenga HTTP client. Those are the options that we found, and those are the options that we considered. And of course, we started by ruling out all the server-side frameworks because this is not what we need. The next we looked was Apache Mina, and Apache Mina was looking very promising because it has both the client and the server NIO libraries. It is kind of evolving from Netty. The problem is that last release was more than a year ago, more than 2 years ago, actually, and this is the contributors graph from GitHub. Doesn't look very promising, basically after 2008. So it won't fly. Next is we're going to get back to the Apache HTTP components. Let's talk about Ning. I don't know how popular Ning is in Europe, but Ning is kind of forums, discussion boards, framework that allows you to create your own communities for your own products. Right, so there are many popular products that use Ning as their discussion forum, and the question is, what the hell, why I'm talking about Ning here? So, in March 3, almost 5 years ago, Ning announced they are developed an asynchronous HTTP client library. Now this looks perfect, it looks exactly what we need, and there is a link here, so we will follow the link and we will get to their great GitHub page which says, okay, we gave it up to Sonatype. And then, you know, we know what to expect from Sonatype, so click here will give us that. Well, that's okay. And then you Google around and ask people, and eventually you can find it. Here it is. Well, actually, it is pretty much alive. You can see this is a relatively up-to-date screenshot, and it is active. People work on it, so it looks very good. And it's time to look to the example usage. And here is the example usage, and let's look at it and see if it's any good. So what do we have here? A client is created, and then we prepare a GET call, we provide some kind of the URL, and then execute gets a closure, and this closure fires events on get called on completed or on throwable. Also, from the future that we get from the execute, we, once the request is completed, can get an HTTP response. Right? So we do have callbacks, and we can get the whole response. Now, this looks very, very good. right? This is exactly what we are looking for. You can imagine how we actually implement those two with the correct code to assemble chunks or, just to download files as a whole, etc., etc. This actually looks very, very good. So let's now look at the last alternative that we didn't speak about, and this is the HTTP components, HTTP async client. This is a relatively new project. It's in version 1 snapshot. It wasn't even released back then. Now they have a 1.0 version, and it does, according to the description, the same as Ning. So what it takes a request producer, it takes a response consumer, and here's the code. So look what we have got here. We create a client, then we start it, we execute a get method, get a future and response, very similar, and then we have a closure that will be called on response received, on byte received, when the releases are resources, and those are the callbacks. There are slight differences from Ning. For example, what the execute will return is up to us to decide. We implement here what the future will return. In this example, I tried to mimic Ning, so I return the HTTP response, but it can be anything. For example, the number of the bytes we managed to download, or the HTTP status code as a string, whatever works for you, and then eventually we can get this response from the get. Right, they are pretty much the same. And that's a good thing. We believe that this is the way to go. This is the right thing to do. And we have a problem. Now we have to decide. They're almost the same. We cannot decide. How can we solve this problem when we have two libraries and we cannot decide among them? Someone wants? What was it? Thank you very much. That deserves money. Here you go. All right, so we don't know how to decide. We throw another layer of abstraction in, and we are all good. This is ours. Of course, we just created an interface that we can implement both over Ning or over HTTP async client. Right, that's what we do. But we still have to decide which one to use. Now we can switch easily, but we need to start with something. So we did a little research, head-to-head. Let's see what we ended up with. So Ning is much more mature than the HTTP async client. HTTP async client is very new, and Ning you saw almost 5 years there. Download cancellation, both of them supported. We had some bugs with HTTP client, but through this bug we learned how responsive the developer is. He provided us a workaround straight away and got it fixed in a matter of days. So actually that was a very good experience with HTTP async client. Progress hooks, here there is a very significant advantage for the HTTP async client. You saw it by the callback, and I'll go back for a second to the callbacks that we saw earlier, and look how granular the callbacks are here. We get information on every byte that we receive. We can choose whether we want to actually act on every byte. But we have this ability. When I'm going to Ning, there is not so much. We only have uncompleted, so we cannot actually implement a progress bar over Ning without changing it at least, right? So that's important as well. Documentation is awful for both of them, but you know, who can complain? We have the sources, we have the tests, we will manage. Server-side counterparts, not that we really care. We won't use it anyhow because we have our own server-side infrastructure already set up, both in Artifactory and Bintray. But having a counterpart means that this is a serious project, that it's taken seriously, and the architecture was well built, because it's almost the same. The differences between the Reactor on the server side and the Reactor on the client sides are minimal, and it makes sense to develop both of them. So it was nice to see the HTTP components server counterpart, although, as I mentioned, it wasn't really mandatory. Another question is performance. So, our answer was, well, we have this layer of abstraction, we don't care, we will just run and see what's faster, but there are benchmarks on the network. Actually, this is from Atlassian blog. They run into the same question that we do and needed to select it. And according to this blog, Apache HTTP async client performs a little bit better, although there are a lot of comments to this blog post, and there are very valid arguments there that this comparison wasn't done in very objective way. So we are not sure. I'm just showing you that. Anyhow, we now have the implementation over HTTP async client, and we are happy with that. Although, as I mentioned, we are ready to switch in any given moment. So that was the first part of our talk today about our experience and what we did. Now let's talk a little bit about the implementation details. So, money question. Who knows what this RFC stands for? 2616? You all know this RFC. HTTP 1.1. No money for you. This is one of the most important RFCs that the network and the internet as of we know it today is based on, right? You all agree to that. And it's not very long, it's under 200 pages long, and whoever deals with network stuff, with internet stuff, with HTTP stuff, is more than advised to just take it and read it. It's definitely worth reading. It's not a thriller, it's not a drama, it's a little bit boring, but it's still a good reading. It's getting confusing sometimes. But then we always have a place to go, which is where we go when we are confused? Stack Overflow. Who Googles those days? We have Stack Overflow. Stack Overflow is a wonderful resource for HTTP knowledge. You can see there are tons of questions about HTTP matters, and once you start asking questions and then you become smarter, you can answer a bit, you can improve your reputation as you go. Stack Overflow is a great resource for HTTP knowledge as well. Now I'm going to tell you a little bit of HTTP war stories about what nasty stuff in this, what looks very trivial protocol we encountered, and I have, I think, 3 more money questions that I will ask on the way. So let's start with the first one. So we use, there are servers that use compression, and let's say we have 1K of a text file, and when I ask for it, server is going to compress it to me to, I don't know, half a kilobyte and send it over. And of course, it's also send the content length header. What the value of that header should be? Should it be a compressed value, or should it be an uncompressed, the original value? What do you say? Who thinks compressed? Who thinks uncompressed? You're all wrong. HTTP 1.1 doesn't give you an answer. So there is a Stack Overflow question, as I already mentioned, with exact this question, and the answer will be, well, it probably will be smaller than 1024, or it might be the compressed size, but we are not sure. There is no clear answer, which actually means no progress bar for you for compressed files, because we don't know when to expect the end. It also means no chunks downloads for you for compressed files, because we don't know whether this chunk is compressed or uncompressed. The answer comes, yeah, that's kind of weird. The answer comes in HTTP2. This is a discussion topic in HTTP2 GitHub project. There is a spec of HTTP2 being written those days in GitHub. This is fascinating. You can watch the discussions, you can join them, it's all open, they accept pull requests and what's not. So this is a very long discussion about it, and the answer is content length will be the compressed size in HTTP 2.0, which makes sense, right? Okay, another one. This one you actually might have a chance to know. So a lot of servers provide you CDN. Bintray is one of them, and when you go to download the file, you start downloading the chunk, and it's getting downloaded good, and then you ask for a next chunk. You ask for a data for a range of bytes from the server, and if it's getting to redirected to CDN, you always start downloading the file from 0, although you asked for a specific range. Why is that? Because of the redirect, which does what? Which wipes out the headers. Thank you very much. This is exactly what happens. And the fix is simple, right? We need to keep the headers on redirect. So this is what we are going to do. We have a builder of the client. We build now a custom client, and we set a redirect strategy to keep the range headers if they exist when the request got redirected. Ning supports that as well. It's kind of a trivial thing. The only thing is you need to know that this happens, and probably until you try it, you won't know that this happens. And if Bintray wasn't used CDN, probably we would discover it later on in production or something. Okay, now this is a very, very funny question. HTTP 1.1, the spec, gives you a number of how many connections a client, browser, or whatever, can open to a single route. Route is the combination of host and a port. Okay, so Nikita wants the money? Right. The answer is 2. A single server shouldn't open more than 2 connections, a single client to a single server, right? Now, it made sense back in, I don't know, what was it? 1998, when the spec was written, but it doesn't make much sense now because you know how it's going. You download the page, and then you need to download all the images, all the JavaScript files from the same server. And then the browsers go, it cannot work with 2 connections. We're going to open like 13 connections and download all the JavaScript and the pictures in one go. And that to improve the load time of the page. Right, so, well, the 2 connections, it's a recommendation. It's a recommendation that doesn't make any sense. That doesn't make any sense those days. Okay, now I have a real money. And I'm going to play it. I need you to bet on how many simultaneous connections HTTP 2 allows. No cheating, no Google, answers now. I need to tear it to many, many parts. 1 is the correct answer, and we are going to talk about why later, all right? Any problems with URL encoding? For me, it will sound like a very simple task. This is what I usually used to do. Do I have some more money here? Yeah. Talk to me. What's wrong with this code? I can hear you. Sorry, maybe the mic will help. In the meanwhile, any ideas what's wrong with this code? No, it's not. It's not double encoded. Oh, no, let's assume it's not encoded. Okay. Yeah, this is a part of it. This is a part of it. And all right, since there are no other suggestions, you will get it. All right. So there are many problems with this code. And the first problem is the encoding is not symmetrical. And I will concentrate only on this part. And look at this code. Look at this code. This has an encoded character into it. It was this guy. Now the question is whether this is a separator between those parameters or it was passed like that because all this is a single parameter. There is no way to know because the encoding is not symmetrical. We cannot go back from the encoded form to the unencoded form, which basically means that when you encode parts of your URL, you need to encode whatever exactly you want to encode and not the whole string. Another problem with URL encoder is that it is not a URL encoder. It's actually encoder of form parameters that are passed from the form post request. There are parameters that come from the post request. They should be encoded. They are not even in the URL. So this is definitely not a URL encoder. It's a form fields encoder. There are very good alternatives in the Apache Commons HTTP client, not related to the async part, of course, but can be used in any code. And there is a URI builder and the URL encoder utils, and they do whatever needed to be done. They allow you to encode correctly the correct parts of it. All right. Next topic. Closing of the connections. Let's talk about that. Now, this is an open question. How do I close a socket correctly? Just close it correctly. There are surprisingly big number of results for this keyword. Have you ever encountered that? The close wait. I did. What is it? This means that the socket wasn't closed correctly. There are at least 3 ways of closing a socket. And I would say it's too many, but this is how it works. So first of all, full close, boom, cutting the connection, no more bytes passing through. The other 2 are half closes. Half closes are much better than full closes, because this is how the real life works. When the shop is going to close, they do a half close. They not lock the customers that happen to be in the last minute on the shop and keep them there until the morning. They actually announce, guys, we're closing the store, finish doing whatever you're doing and get out, and we're not accepting new customers now, but we will let you out. It's actually the same with HTTP connections. Half close is that. We don't accept any new connections, but we will wait to the current connection to finish. And this is how it should be done. Now, the biggest problem, the biggest bad thing that can happen, and we did it, is blocking inside a close method. Blocking inside the close method does exactly that. It leaves your customers in the store forever, because after a very short while, the server gets up on you and say, you know what, I'm not waiting for those guys. I'll lock them up until the morning, and that's no problem with me. And this is what happens, and this is a problem for a connection leaking, because it's not being closed correctly and it's getting accumulated more and more open sockets. The good news is we don't care. Since Java 7, we have a very nice way to deal with all the closing problems of everything, maybe except of the shops. But everything is code is now very, very simple. We just wrap it with try with resources. And then we don't care what the close does, assuming it is closed correctly, and guess what? It is closed correctly then. So just use try and resources and you will be good. Another problem is writing parts concurrently. So there are two strategies. One is to write to separate files and then combine the results on finish. The other is writing to the same file, seeking to the right position afterwards. Right? And of course, the second is more beneficial because you don't want to see those temporary files flying around and then you cancel, they are not getting deleted. Not fun. Instead, we will open a file and write to the same places in it, and that's of course the preferable way. So how do you do it? Whoever took the Java certified programmer exam knows how to do it. You use the Java random access file, and well, you don't. There is a page that's called random access file in the Java tutorial, and the page that is called random access file advises you not to use random access file. Because, the name remains from Java 4, but now we have new IO with seekable byte channel. And seekable byte channel, as opposite to random access file, is thread safe, is much more efficient, and performs generally better. So the topic random access file advises you to use the seekable byte channel. We use something that is close to it. It's called the file channel, which implements the seekable byte channel interface, and it has a write method that gets the bytes that need to be written and the position where to start. The API is pretty much the same, works much better. We need to track the download process, so we implemented this very complicated serialization of our own. We have a text file with file names and the parts just by them, very complicated stuff, and this is how we track the progress of each and every file. Couple of words about file locking. I'm running out of time, so we will do it rather quickly. There we have two levels of file locking. The virtual machine level, so we want to write to the same file from the same Java process, and operation system level that should prevent writing to the same file from different processes. So we need both. We need the operation system file locking for preventing multiple download instances trying to download the same file and writing to the same file. So we have two of them, so I want to write to the same file here, right? And this is why we need it. We can get a file lock, and this is a file system, operation system file lock. And then, if we can't get it, we just throw overlapping file lock exception and cancel the download. The problem is this should be read lock. I mean, we still need to be able to read this file even if someone else is writing it. The problem is here we can select it to be shared to write through here, but it won't work on Windows anyhow. You know why? There is a very neat trick, and I will just show it to you for the fun of it. This is how it actually needs to be done. We don't lock the file. We lock the last byte before the long max value in memory, which means somewhere, which actually means we don't lock anything, we just try to get the lock from two files on the same memory location. And then the file is still readable because we actually didn't lock it, but we're still able to to throw the overlapping lock exception if we cannot occur this lock twice. So the file is readable, but it's still locked. And this is a good way to find it. This is one of the Stack Overflow gems I mentioned earlier. VM-level locking. At first, it looks like we don't need it because we always write to different parts of files. We never overlap. So why do we need it? We actually need it for a single reason. We need to synchronize the closing procedure of a file. We have a relatively complicated closing sequence. We need to release the operation system file logs, close the channels, rename the file from being .part to being the actual file, and erase this file that tracked the progress info. It's not rocket science, it's not very difficult, but those are not atomic operations. So for that, we need to prevent it. Now, this is a very simple code. If you ever used reend and read-write lock, this is exactly what you did. So there is not much to talk about it. What I want to use for the remaining 2 minutes is to talking about the future. Well, and the future is HTTP 2 with a very strange name. You know, everyone tries to find some nice way to write version 2. This is how HTTP guys do it. From the user perspective, from the browser perspective, you probably won't see any breaking changes in the way you work with HTTP, but HTTP 2 is mostly about standardizing the Google Speedy protocol. Nice features is the header compression, for example. Back in the HTTP 1.1 days, no one even think about compressing the headers because, you know, the headers. Today we see that sometimes the headers part is bigger than the body part. So it's definitely, and it's plain text, it's definitely worth compressing. Multiplexing, I'm going to show you a slide about it in a second. Prioritization, server can now decide which clients should be prioritized over another ones. Server push, this is the server socket part, right? All this notion of server being able to push additional files to client. This is very powerful because now you download the HTTP as a client and get all the servers, all the files from the server by server itself. You don't need to do additional requests. The only thing is, of course, your client need to be prepared on it. Server is going to throw files on you, right? So all the modern browsers, at least, and their beta versions, already support it, and it's really cool. And on the way, they are going to clear uncleared questions. One of them is the one that I mentioned earlier with compressed, uncompressed size. Right. This is the multiplexing. And the multiplexing goes like, I'm going to open one connection instead of having many, and going to get all the data going there. It will be both the HTTP page and the JavaScript that it needs and all the pictures that it needs, and everything is going to be loaded on the same pipe. Instead of having many small pipes, we will have one big pipe, and the client will sort it over and know what part of what is going on it. They did a very, very massive test. They have huge labs with huge network devices and machines, and this is going to be much faster. Expect much faster loading times for almost any page with HTTP 2, and those are great news. This talk, of course, the slides will be available online, so you will have all the links working, and of course, HTTP 1.1, great book, HTTP The Definitive Guide. It's old, but the protocol is old, so don't get scared by seeing the time of this book. The Reactor part and the recording of the talk that I mentioned earlier of Doug Lee on Nile. So thank you very much. Now for the money, whoever got the monopoly money, come and I will give you real money instead. How that sounds?
Okay, now it's the coffee break.